Hello! In this video, we are going to prove the following theorem. Suppose A is a set, A is an element of A, and G is a function from A to A. Then, there is a unique function f from the natural numbers to A, such that f of 0 is equal to A, and f of the successor of n is equal to g of f of n for all natural numbers n. So essentially, what this function f is doing is it's saying f of 0 is equal to A, f of 1 is equal to g of A, f of 2 is equal to g of A, f of 3 is equal to g of A, and so on. This theorem is often referred to as the recursion theorem. Now, before we get into proving this theorem, let's first remind ourselves of how we've constructed the natural numbers so far. First of all, if A is a set, then the successor of A is given by the union of A in the singleton set of A. And next, a set I is said to be an inductive set if the empty set is an element of I, and for every element n in I, the successor of n is an element of I as well. Now, a natural number is a set which belongs to every inductive set. And at this point, we have proven that there exists a set whose members are exactly the natural numbers. And we denote that set by the Greek letter omega. And we have proven that the set of natural numbers is an inductive set. So in that case, that means that the empty set is an element of omega. And for every element n in omega, the successor of n is an element of omega as well. Now, from now on, we are going to define the natural number 0 to be the empty set. Now, another property that we've proven about the natural numbers is the principle of induction, which says the following. If S is a subset of the natural numbers and S is an inductive set, then S is equal to the set of natural numbers. And two other important properties of the natural numbers that we have proven are the following. We have that 0 is not the successor of any natural number, and for every two natural numbers, m and n, if the successor of m is equal to the successor of n, then m is equal to n. And the contrapositive of this is saying if m and n are distinct, then the successor of m and the successor of n are distinct. Now, these 5 facts tell us that the set of natural numbers forms a Peano system. And so we're going to be using that to prove the recursion theorem. So now, let's get into proving the recursion theorem. For the proof, the idea is we consider the following set. We consider the set S, which we define to be the set of relations P from omega to A, such that 0, A is an element of P, and for every natural number n and every element x in A, if n, x is an element of P, then the successor of n, g of x is an element of P. Now, we can show S is non-empty, because in particular, we can show that omega times A is an element of S. To show that omega times A is an element of S, well, replacing P with omega times A, it is clear that omega times A is a subset of omega times A. So omega times A satisfies the first condition. And then, since 0 is an element of omega, and A is an element of A, that implies 0, A is an element of omega times A. So omega times A satisfies this condition. And it's also clear that omega times a will satisfy this condition. Because if we consider an arbitrary natural number n and x in a, well, it's true, since n is an element of omega and x is an element of a, we have n comma x is an element of omega times a. So this is true. But then, since n is an element of omega, it follows that the successor of n is an element of omega. Since x is an element of a, when we send x into the function g, the alpha value g of x will be an element of a. So, successor of n is an element of omega, g of x is an element of a, therefore successor of n comma g of x is an element of omega times a. So this statement is true as well. So we see both of these statements are true, and if true, then true is a true statement. So this conditional is true. Therefore, omega times a satisfies the third condition, to be an element of S. So omega times a satisfies all the requirements to be an element of S. And so S is non-empty. But if you recall, whenever we have a non-empty set, let's say T, well then, there exists a set which we'll call the intersection of T, which has the following property. For all x, to say that x is an element of the intersection of T is equivalent to saying that x belongs to every set in T. So in other words, we have for all y in T, x is an element of y. So, since S is non-empty, there exists a set called the intersection of S, which satisfies this property. And we're going to say that the intersection of S is equal to F. So remember, to be an element of the intersection of S means that you're an element of every set in S. And the claim is that this choice for F will be a function from the natural numbers to A, and it satisfies these two properties. Now, before we get into showing that F satisfies any of these properties, we're first going to show that F is an element of S. To show that F is an element of S, well, in the definition of S, let's replace P with F. So we want to show that F satisfies these three properties. Let's first show that F is a subset of omega times A. To prove that, let's consider an arbitrary element of F. I'll call it P. Well, if P is an element of F, this means P is an element of every set in S. So in particular, P must be an element of omega times A. So this shows if P is any element of F, then P is an element of omega times A, and therefore F is a subset of omega times A. So F satisfies the first condition to be an element of S. Now let's show 0, A is an element of F. To show that 0, A is an element of F, we want to show that 0, A belongs to every set in S. So to prove that, well, if we consider an arbitrary element of S, I'll call it P. Well, since P is an element of S, well then 0, A is an element of P. So this shows if P is any arbitrary element of S, then 0, A belongs to P. So 0, A belongs to every element of S, and therefore 0, A belongs to F. So F satisfies the second condition as well. So to prove the third condition, let's give ourselves an arbitrary natural number n, an arbitrary element x in A, and we'll suppose n, x is an element of F. From here, we would like to show that the successor of n, g of x is an element of F. Or in other words, we want to show that the successor of n, g of x belongs to every set in S. So to show that, well, if we consider an arbitrary set in S, call it P, well, since n, x is an element of F, this means n comma x belongs to every set in S. So in particular, n comma x must belong to P. But then, from the fact that n is a natural number, x is an element of A, and n comma x is an element of P, since P is an element of S, these three facts imply the successor of n comma g of x is an element of P. So this shows if P is any arbitrary element of S, then the successor of n comma g of x is an element of P. And therefore, the successor of n comma g of x belongs to every set in S. And therefore, the successor of n comma g of x belongs to F. So now, putting this all together, we see if n is an arbitrary natural number and x is an arbitrary element of A, well then, if n comma x is an element of F, then the successor of n comma g of x is an element of F. So that proves that F satisfies the third condition to be an element of S. So F satisfies all requirements to be an element of S. So F must be an element of S. Now our whole goal is to show that F is a function from omega to A and satisfies these properties. Now to show that F is a function from omega to A, what that means is we're trying to show that the following is true. We're trying to show that F is a subset of omega times A, and for every natural number n, there is a unique x such that n comma x is an element of F. Now we already know that F is a subset of omega times A. We showed that right here. So all that's left to show is the property which will tell us that F is a function from omega to A. Now, we can expand this statement out a little bit. To say that there exists a unique x such that n comma x is an element of F can be expanded out into two parts, an existence part and a uniqueness part. The existence part is that there exists an x such that n comma x is an element of F. And the uniqueness part is that if y and z are any two sets such that n comma y and n comma z are elements of F, then y and z must be equal. Now, we could expand this out further because the universal quantifier distributes over conjunction. So this is equivalent to saying for all natural numbers n, this is true, and for all natural numbers n, this is true. So we've essentially just distributed the universal quantifier to the existence part and the uniqueness part. So essentially we have two statements we are going to prove. We're first going to prove the existence statement, and then we're going to prove the uniqueness statement. To prove the existence statement, we consider the set consisting of the natural numbers n such that n comma x is an element of F for some x. And the claim is that C is equal to the set of natural numbers. To prove that, we can use the principle of induction, which tells us all we have to do is show that C is an inductive set. And to prove that, we want to show that 0 is an element of C, and then we want to prove if n is any element of C, then the successor of n is an element of C. So let's start out by showing 0 is an element of C. To show that 0 is an element of C, we need 0 to satisfy these two statements. Well, we know that 0 is a natural number, so what's most important is that we prove 0 comma x is an element of F for some x. Well, actually, we know that 0 comma a is an element of F, so this statement is automatically true as well. So now let's show if n is an arbitrary element of C, then the successor of n is an element of C. Well, that means n is a natural number and n comma x is an element of F for some x. And since F is a subset of omega times A, from the fact that n comma x is an element of f, that tells us x must be an element of A. So now, since n is an element of omega, x is an element of A, and n comma x is an element of f, it follows from the fact that f is an element of S that the successor of n comma g of x is also an element of f. And so this tells us that the successor of n comma something is an element of f. So that tells us that the successor of n satisfies this condition, right? Because if we replace this guy right here with the successor of n, well, the successor of n satisfies this condition because successor of n comma something is an element of f. So successor of n satisfies this condition. Of course, since n is a natural number, it follows that the successor of n is a natural number. So successor of n satisfies this condition as well. And therefore, successor of n satisfies all requirements to be an element of C. And so, by the principle of induction, we can conclude that C is equal to the set of natural numbers. And since this set is equal to the set of natural numbers, that tells us that this statement is true. Because if we considered an arbitrary natural number n, well then n is an element of C. So we have that there exists an x such that n comma x is an element of f. So that's true. So we have shown that the existence portion is true. Now we're going to prove the uniqueness portion. So since we've ran out of room, we're going to move back into the top and we're going to prove the uniqueness portion. So to prove this statement, the idea is we consider the following set. We consider the set of natural numbers n such that this is true. We're going to call that set D. The claim is that D is equal to the set of natural numbers. And to show that D is equal to the set of natural numbers, we are going to use the principle of induction. So let's first show that 0 is an element of D. To prove that 0 is an element of D, well, let's assume for a contradiction, 0 is not an element of D. So since we're assuming 0 is not an element of D, this means that this statement cannot be true for 0. So the negation of this statement is true for 0. And the negation of this statement for 0 would be to say that there exists y and z such that 0 comma y and 0 comma z are elements of f, but y is not equal to z. Now, the observation here is that at least one of these guys is distinct from A. Because on one hand, if y is not equal to A, well then, y is not equal to A, and 0 comma y is an element of f. On the other hand, if y is equal to A, well, since y and z are distinct, this means z must be distinct from A. So z is distinct from A, and 0 comma z is an element of f. So what we see here is, no matter what, there must exist an object B such that B is distinct from A, and 0 comma B is an element of f. Right? No matter what, this statement is true. Because in the case where y is not equal to A, we just take B to be y. In the case where y is equal to A, we just take B to be z. So yeah, no matter what, this statement is true. And we know that f is a subset of omega times A, which means B must be an element of A. But now, to reach a contradiction, the idea is we consider the following set. We consider the set F with the ordered pair 0, b removed, and we call the set F1. The claim is that F1 is an element of S. To show that, well, in the definition of S, let's replace P with F1. And let's first show that F1 is a subset of omega times A. To do that, if we consider an arbitrary element, P in F1, well, since P is an element of F1, that implies P is an element of F. And we know that F is a subset of omega times A, so that implies P must be an element of omega times A. So this shows if P is any element of F1, then P must be an element of omega times A, and therefore F1 is a subset of omega times A. So F1 satisfies this condition. Now let's show 0, A is an element of F1. To show 0, A is an element of F1, we want to show that 0, A is an element of F, and 0, A is not equal to 0, B. Now we know that 0, A is an element of F. That comes directly from when we showed F was an element of S. One of the things that we showed was that 0, A was an element of F. But also, since A and B are distinct, there's no way that 0, A could be equal to 0, B. So we see that 0, A is an element of F, and 0, A is distinct from 0, B. So 0, A must be an element of F with the ordered pair 0, B removed. Or in other words, 0, A is an element of F1. So this shows that F1 satisfies this condition. So now we want to show F1 satisfies the last condition. To prove the last condition, let's give ourselves an arbitrary natural number n, arbitrary element x and a, and we'll suppose n, x is an element of F1. Well then, since n, x is an element of F1, it follows that n, x is an element of F. So, since n is an element of omega, x is an element of A, and n, x is an element of F, it follows from the fact that F is an element of S that the successor of n, g of x is an element of F as well. But also, we know that 0 is not the successor of any natural number. So in particular, 0 is not the successor of n. So since 0 is not equal to the successor of n, there's no way that the successor of n, g of x is equal to 0, b. So what we see here is that the successor of n, g of x is an element of F, and the successor of n, g of x is not equal to 0, b. So the successor of n, g of x must be an element of F with 0, b removed. So in other words, it's an element of F1. That shows that F1 satisfies the final condition to be an element of S. So F1 is an element of S. But then here's where the contradiction comes in. Since 0, b is an element of F, and F is the intersection of S, this means that 0, b belongs to every set in S. So in particular, 0, b must belong to F1. But that contradicts the fact that F1 has 0, b removed from it. Our assumption that 0 is not an element of D leads to a contradiction, so we must instead have 0 is an element of D. So we've shown that 0 is an element of D. Now we're going to show for an arbitrary element n in D, the successor of n belongs to D, because that will prove by induction that D is equal to the set of natural numbers. So let's give ourselves an arbitrary element n in D. Now, we've already proven the existence part, so we know that there exists an x such that n, x is an element of F. And since F is a subset of omega times A, we know x is going to be an element of A. Now, of course, we know that n is a natural number, and x is an element of A, and n comma x is an element of F. So, from the fact that F is an element of S, this implies the successor of n, comma g of x, is an element of F. Now, the whole goal is to show that the successor of n belongs to D. And to prove that, assume for a contradiction, instead, the successor of n does not belong to D. Well, then in that case, this statement is not true for the successor of n. Instead, the negation is true for the successor of n. So in that case, there exists a y and there exists a z such that the successor of n comma y and the successor of n comma z are elements of F, but y is not equal to z. Now, the thing to observe here is that at least one of these guys is distinct from g of x. Because on one hand, if y is not equal to g of x, well then, y is not equal to g of x. And we have the successor of n comma y is an element of F. On the other hand, if y is equal to g of x, well, since y and z are distinct, this implies z and g of x are distinct. So z is not equal to g of x, and also we know that successor of n comma z is an element of F. And so what this shows is, no matter what, there exists an object, u, such that u is distinct from g of x, and has the property that the successor of n comma u is an element of F. Right? In the case where y is not equal to g of x, just take u to be y. In the case where y is equal to g of x, just take u to be z. So, no matter what, this is true. The idea to reach a contradiction is to consider the set F with the ordered pair successor of n comma u removed. And the claim is that F2 is an element of S. And so to prove that, let's replace P with F2. And so let's first show that F2 is a subset of omega times A. Well, to do that, if we consider an arbitrary element P in F2, well, since P is an element of F2, we know that P is an element of F. And since F is a subset of omega times A, that implies P is an element of omega times A. So this shows that any element of F2 will also be an element of omega times A, and therefore F2 is a subset of omega times A. So F2 satisfies this condition. We can also see that 0 comma A is an element of F2 because, well, first of all, we know 0 comma A is an element of F. And since 0 is not the successor of any natural number, then in particular, 0 is not the successor of n. Well, since 0 is not the successor of n, well, then there's no way that 0 comma A could be equal to the successor of n comma u. So this shows that 0 comma A is an element of F, and 0 comma A is not equal to the successor of n comma u. So 0 comma A must be an element of F with the successor of n comma u removed. Or in other words, 0 comma A is an element of F2. So that shows F2 satisfies this condition. So now let's prove F2 satisfies the final condition. To prove the final condition, we're going to give ourselves an arbitrary natural number m and an arbitrary element t in A. And we'll suppose m comma t is an element of F2. The reason why we're calling them m and t instead of n and x is because we already have n in our proof right here, and we already have x in our proof right here. So the whole goal is to show the successor of n comma g of t is an element of F2. To prove that, well, since m comma t is an element of F2, it follows that m comma t is an element of F. And since m is a natural number, t is an element of A, and m comma t is an element of F, it follows from the fact that F is an element of S that the successor of m comma g of t is an element of F as well. So we've shown that the successor of m comma g of t is an element of F. So all that's left to show is that it's not equal to the successor of n comma u. And to prove that, we're going to split this up into two cases. Either m is equal to n, or m is not equal to n. Let's first consider the case m is equal to n. If m is equal to n, well then we have this ordered pair can be re-expressed as n comma t, so n comma t is an element of F. But remember, we're assuming n is an element of D, which means the uniqueness portion holds for n. So since we know n comma t is an element of F, and we know n comma x is an element of F, it follows that t is equal to x. So what does this mean? Well, let's write out the ordered pair successor of m comma g of t. What we can do here is we can replace m with n, since they're equal. So this is successor of n, but since t is equal to x, we can replace g of t with g of x. And since we know g of x and u are distinct, there's no way that successor of n comma g of x could be equal to successor of n comma u. So this is distinct from successor of n comma u. So we've shown that successor of n comma g of t is distinct from successor of n comma u, which is what we wanted to show, right? This completes the case m is equal to n. We're going to show that the same thing is true in the case where n is not equal to n. If m is not equal to n, well, remember, distinct natural numbers have distinct successors. So the successor of n is distinct from the successor of n. So there's no way that the successor of m comma g of t could be equal to successor of n comma u in this case either. And so that completes the case that m is distinct from n. So what we see here is, whether we have m equal to n or m not equal to n, we always have successor of m comma g of t not equal to successor of n comma u. So putting this all together now, we have shown successor of m comma g of t is an element of F, and successor of m comma g of t is not equal to successor of n comma u. So successor of m comma g of t must be an element of F2. And so that overall proves that the third condition is true for F2, because we've shown if m is any natural number and t is any element of A such that m comma t is an element of F2, it follows that successor of m comma g of t is an element of F2 as well. So that proves the final condition. So F2 is an element of S. But now here's where we reach the contradiction. Since the successor of n comma u is an element of F, and F is the intersection of all sets in S, well, that means successor of n comma u belongs to every set in S. So in particular, successor of n comma u must belong to F2. But this contradicts the fact that F2 is the set F with successor of n comma u removed. Our assumption that the successor of n is not an element of D led us to a contradiction. So we must instead have that the successor of n is an element of D. And that's it. So by the principle of induction, D must be equal to the set of natural numbers. And because this set D is equal to the set of natural numbers, that means that the uniqueness part must be true, right? So we're done. This proves that our choice of F is in fact a function from omega to A. So now we're going to show that F satisfies these properties. Well, actually, that comes pretty easily, because we know that 0, a is an element of f. So, writing this in this form, we have f of 0 equals a. But now, to show that this statement is true, let's give ourselves an arbitrary natural number n. Well then, if we send n into the function f, the output value is f of n, which is an element of a. And we also know the ordered pair n comma f of n is an element of f. But then, since n is a natural number, f of n is an element of a, and n comma f of n is an element of f. Since f is an element of s, that implies the successor of n, comma g of f of n, is an element of f as well. Right? We're really just applying the final portion of the definition of s to f. But since f is a function now, we can rewrite this by saying f of the successor of n is equal to g of f of n. So we've shown if n is any natural number, then f of the successor of n is equal to g of f of n, which is exactly what we wanted. So we have shown that our choice of f satisfies these properties. So now we want to show that f is the unique function which satisfies these properties. And to prove that, well, we're trying to prove uniqueness. Let's suppose we have two functions. I'll call them f prime and f prime prime, which are both functions from omega to a, and they satisfy these properties. To prove uniqueness, we want to show that the functions f prime and f prime prime are equal. And to prove that these two functions are equal, what we can do is we can show for all natural numbers n, f prime of n is equal to f prime prime of n. To prove that, we consider the following set. We consider the set E, which is the set of natural numbers n such that f prime of n is equal to f prime prime of n. The claim is that E is equal to the set of natural numbers. And we're going to prove that using induction. So first, to show that 0 is an element of E, well, we know that f prime of 0 is equal to a, and f prime prime of 0 is equal to a, and therefore f prime of 0 must be equal to f prime prime of 0. And because of that, we immediately have that 0 is an element of E. So now, let's suppose we have an arbitrary element n in E, and from there we're going to prove the successor of n is an element of E. So with an arbitrary element n in E, that means that n is a natural number such that f prime of n is equal to f prime prime of n. Now to prove that the successor of n is an element of E, we want to show that f prime of the successor of n is equal to f prime prime of the successor of n. Now remember, this statement is true for every natural number n. So since n is a natural number, this statement is true. Similarly, this statement must be true. So what do we see here? We see f prime of the successor of n is equal to g of f prime of n. But remember, f prime of n is equal to f prime prime of n. So we can substitute f prime of n here with f prime prime of n, but g of f prime prime of n is equal to f prime prime of the successor of n. And so this shows that f prime of the successor of n is equal to f prime prime of the successor of n. And so that shows that the successor of n is an element of E. And that's it. So by the principle of induction, that tells us that E is the set of natural numbers. And because E is the set of natural numbers, this means for every natural number n, f prime of n is equal to f prime prime of n. Or in other words, these two functions, f prime and f prime prime, are equal. And so that proves that the function f, which we found to satisfy these conditions, is unique. So we have proven the theorem. So this completes the proof. And so yeah, that's pretty much it for this video.